Okay, so today's focus is going to be on subquadratic algorithms, subquadratic sorting algorithms. So what we mean by subquadratic is that algorithms that perform it at n log n complexity. We have looked at some of the naive algorithms that are n squared complexity, such as bubble sort, selection sort, insertion sort. So now we're going to argue or learn about the this n log n algorithm, new algorithm called the quicksort. It turns out that the quicksort was it was developed in the 60s, and it's the fastest known algorithm for sorting a random set of data. So some of the facts about quicksort are it is the fastest known algorithm for sorting a set of random data. Interestingly, many people worked on sorting algorithms, but no one has been able to come up with the right kind of conditions for the algorithm to go really fast. From an asymptotic complexity point, quicksort is also n log n as merge sort, but it seems that in most cases the quicksort seems to outperform the merge sort. That's an interesting observation. So in practice, quicksort is the best, fastest known algorithm in practice. Okay, and the basic idea of quicksort is the following. Now you pick a pivot element, whatever the pivot element, and then you find a way to put the pivot element into the right place. That means pivot, that's where the pivot is, that's where the element's supposed to be in a sorted array, such that all the things that are less than to the pivot is on this side, all the things that are greater than or equal to the pivot are on this side. So ideally what we are saying is that if you call this low and if you call this high, what we're saying is that if you take the array segment from low to the pivot location, all right, so if you take the pivot location not included, then we don't know that the okay, so this is pivot location. This is all the elements in that segment are less than the pivot. So let's call this pivot location. And the same thing with this side here, all the elements, if you take all the elements from pivot +1 to the high, not included, and those are greater than or equal to the pivot. So those are some of the two invariants that we think should be true if we can find a way to partition this and get this array sorted. So the idea of quicksort is helps us find the asymptotic complexity of partitioning and eventually the complexity of the quicksort. Now the partitioning process seems to be easy to understand. What you're looking for is, given a pivot, you're trying to find some things, you're trying to do a rearrangement, a permutation of the same arrays such that things that are less than onto the other side, things that are greater than or equal to the other side. We don't make any guarantees about the left and the right subarrays that are not sorted yet, but we do know that this is in the right place. The pivot is in the right place. Now it seems that we can find a reasonable algorithm to do this in big O of n in linear time. You just have to scan the array once, and we should be able to do that in big O of n time. And we also do know that the when you do the quicksort, what you do is you do it recursively. That means you take this array segment and then you find a pivot from that, and then you do the same thing, and you take this array segment and find a pivot from that, and depending on how good the pivot is going to be, your partitioning is going to be much better. So ideally we'd like to have the pivot to be the median. Then you would divide this in the middle exactly, and then you can assume that you can have log n height tree if we can do that. So it's clearly, if you do log n work in the partitioning stage and log n height, log n levels, then you can argue easily that your performance of this algorithm must be n log n. But unfortunately the quicksort can go bad. Most likely the scenario would be that you're trying to sort a sorted array, which is, we don't know that's sorted, so we're trying to sort it. We pick the pivot to be the minimum element. So in this case, the tree would be like this. You have an array of size 1, and then the other array that is not sorted is of size n minus 1. Then you happen to pick this element again here, and you have an array of size 1 here and an array of size n over 2. So if you keep doing this, it's clear that this can be as bad as big O of n. And because the partitioning take big O of n to partition, so we assume that the quicksort in the worst case scenario, the worst case scenario is whatever the scenario that leads to uneven partitioning. In this case, these are the extreme partitioning, because partitioning is kind of like not breaking into two things that are almost of equal size. It's kind of breaking it in a way that's not going to give us any kind of advantage of having a log n performance. So what people try to do is to avoid the worst case. So one of the ways to avoid the worst case is to randomize the data set. Okay, so to avoid the worst case, you can randomize the data set before you apply the quicksort, or you can pick a good pivot. People take the median of the three. Median of the three means you take the first, last, and the middle, and you find the median. So it turns out that that strategy is a good strategy. It's a heuristic, and it's a good strategy perhaps in practice, that it gives you even partitioning among the recursive array subarrays. So if you take a snapshot of the partitioning algorithm, which is really the big deal here, because if you can do the partitioning correctly in big O of n time, which is what we expect, then we have a good algorithm, and all we have to make sure is that the pivoting will break the array into almost two equal subarrays. So if you look at the picture here, what you see is that if you take the array segment from lower to the left, and all of that is strictly less than the pivot, which happens to be equal to 4. And if you take the ace of left to right not included, notice right is the next one to look at, and it turns out that this is greater than or equal to pivot, and that happens to be 4. So ideally this is the kind of invariance you need. Lower to left, we know it's all of them are less than the pivot. Left to right, all of them are more than the pivot. So by the time the right reaches the final element, then we have already established the fact that the pivot, wherever the pivot is going to be, should be in the right place. Okay, so how do we begin this algorithm? Let's try to trace a piece of code here. So let's take a look at how the partitioning is done. This is the big idea of quicksort. We got to find a good way to partition this in big O of n time. So ideally what we like to have is not to do too many swaps when we do partitioning, and keep finding ways to minimize the amount of swaps you're doing. So the basic idea is that you maintain two pointers, right and left, and initially they are both pointing to the same element, the first element or the lower element, and the only time you swap is if your right happens to be less than the pivot. So if the right happens to be less than the pivot, perhaps we should do a swap to bring the right to the correct place. So we've swapped the ace of right and ace of left, because we do know that the things to the left are less than the pivot. So we should bring the left element and the right element should be swapped. So so the only thing we are always looking at is the right ace of right. So let's take a look at how this works. And so you start with left and right pointing to the same thing, and ace of right is clearly less than the pivot because pivot happens to be the number 4. And so what we need to do is we're going to swap the ace of right and ace of left. In this case nothing happens because they're both pointing to 2, but we move the left and the right pointers then to the right by 1. So left and the right will go to this location. Now if a sub right, which happens to be 4, is greater than or equal to the pivot, then all we need to do is to move the right pointer to the 1 to the right by 1. Look at a sub right. A sub right is now less than the pivot, so this is the time for us to do a swap. So what we do is we swap 1 and 4. Swap 1 and 4 here, and then we move both the left and the right pointer to the right side. Okay, and so let's take a look at the right pointer now. Right point is greater than or equal to the pivot, so right pointer can move to the next element. Now the right point is less than the pivot, so at this point we should do a left and the right swap. So in this case the 4 will come here and the 3 will go there, and then we will increment the left pointer, and then we will increment the right pointer. Now right pointer keeps moving forward as long as it's a right is greater than or equal to the pivot. So obviously right pointer will go to 7 to 9, and then we'll stop here next. At this point the right point is less than the pivot, so we must do a swap between 7 and 0. So 0 comes here, 7 comes here, and then we should move the left and the right pointers to the right by one place. And so right is now pointing to 6. Now the right will continue to move to the right. We'll move to 1, and at that point the right pointer is less than the pivot, strictly less than the pivot. So we must do a swap between 1 and 4. So the 1 comes here, and the 4 comes here, and the right moves to this location, and the left moves forward. So left is now pointing to 8. Now let's keep moving. So the 9 will go, because 9 is greater than the pivot, right will continue to move. Now the 4 is greater than the pivot, greater than or equal to the pivot, so it will continue to move. 8 is greater than or equal to the pivot, it will continue to move. So now we come to a place where we need to do a swap between this and the left. Now the left is, notice the pointing to 8, so I'm going to do 8 here, and I'm going to do 3 here. And the left now should move one place to the right. So at this point the right has come to the final location. And so the only thing remaining to do is take the left element and then swap that with the pivot. So you will get 4 here, and then we do know that the 4 is in the right place now. 7 goes here, and the remaining elements, if you write it down, are 2, 1, 3, 0, 1, 3. And then these elements are 9, 7, 6, 4, 9, 4, 8, 8. Okay, so here's how the array looks like, and clearly this side is less than the pivot, and this side is greater than or equal to the pivot. So now we can do the recursive process on the on this subarray as well. Okay. So so the next so this gives us an idea about how to do the partitioning. Notice that we don't promise anything about these two subarrays. We don't promise anything about these two subarrays. And so the next is to develop the code. So we look at the starter code, and the starter code goes like this. If you start with the lower and the upper, if the array size, which is given by the upper minus the lower, is less than or equal to 1, there's nothing to do. And otherwise we will partition the lower to upper and find an index, and that means we have an index where we will find the a sub I is in the right place. So a sub I is done, and then you look at the lower to I, and then you look at the I plus 1 to upper. So you keep performing this operation. So this is a real simple quicksort code. Now the partitioning code is, if you develop, then you have several preconditions. The lower is strictly less than the upper, notice that, and then the result that we get should be between lower and the upper not included. And we also make sure that the result when we get the result, that means whatever the partition, the location that we get, that location, anything to the lower to result. So if you take the this array segment, if you take the lower to result not included, now that segment is less than ace of the result. So that's what that's one of the invariants. So the other side is less than or equal. That's the right hand side of things. And then so in this case we put the pivot index to be the middle element as usual, like the same concept as the merge sort. And then we swap the pivot with the last element, the upper -1, and then we start with left and the lower, and then we will just try to do the if the pivot is less than or equal to ace of right is greater than or equal to pivot, you move the right. Otherwise you swap the left and the right and move the 2 pointers there. At the end you're going to swap the left element with the upper -1 in the way I showed it in the previous slide there. Now a bunch of invariants are true, that at any given point the pivot must be greater than the lower to left. So if you take the array segment from lower to left, the pivot must be greater than that, and the pivot must be less than or equal to the ace of left to the right. And the loop invariant, you can also take a loop invariant which is always the pivot is a upper -1, because we don't really change the pivot until we go out of this loop. So we got a bunch of loop invariants that we can prove, and perhaps we can use them to prove the correctness of the algorithm. So this ends the sort of a quick intro to quicksort, but we will talk about more details in class.